Hello, everyone. My name is Mario Gonzalez. I'm a senior applications developer at Ogilvy in Mather, New York. And I'm going to be talking about real-time multiplayer games with Node.js. For the Ogilvy's 2011 holiday card, we decided to make an HTML5 game. And having heard a lot about Node.js and Socket.io slightly, we decided that we should create a multiplayer game. The game is currently located at holiday2010.ogilvy.com, and I'm going to briefly just try to play it and see how it looks, and let's see how that goes. So let me move this over here. Oops. So this is the game. I'm going to just jump in, select a character. That guy's fine. And then I'm going to open up a new tab and do the same thing. Give me 1 second here. Oh, there you go. Somebody else is playing right now. So slide it over, maximize. So this is an example of a game that we created. The game runs on Canvas, and then the multiplayer engine is created using Node.js and WebSockets on the browser side. So I'm going to talk a little bit about how we went about creating this game, some problems that we faced, and a framework that we created recently, which abstracted the difficult networking stuff out of this game, and we've released it onto GitHub earlier this week. And goodbye. So the benefits of writing your game with JavaScript and Node.js, one of them is that JavaScript is actually a really great language for writing games. Has all of the tools that you need in order to write a game concisely, and you can play around with a lot of different things because you're not held back by allocation of memory, and you don't have to worry about the stack versus the heap. Node.js and V8 are extremely fast. In our game, the node process was using only one thread, and it runs at about 3 to 4 CPU usage while running 8 simultaneous games, each with their own collision engine instance. Because the client and the server are both running in JavaScript, you get great interoperability between the client and the server. There's no translation layer that you need to apply because the world state exists in some sort of data on the server side and exists in different data on the client side, and you need to translate that when they communicate with each other. An example of this is, for example, if you have a vector math utility class, you can just outright use that class in both sides of the game. This is an example of the interoperability between the client and the server. This represents the net channel message class, which actually is just a value object that contains some data. But we didn't have to write anything to turn that into something the server understands and then turn it back to what the client understands. It's all JavaScript. So that's pretty cool. Now let's write a game. We had a couple of problems that arose, but the one that I'm going to be talking about today is the problem that we face, that's faced by all real-time multiplayer games, and that is dealing with latency. The initial naive approach is to package up the client's information and then send that to the server, and then the server will send that same message off to all of the other clients. And that works fine in a system where you have trusted clients, such as a military simulation. But in a real game on the internet, that approach starts to break down. And the reason why is that the main problem with this approach is that we cannot trust users to provide us with correct information about their player's current state. If you ask a nefarious user and he enters a game where his projectile is, he'll tell you it's everywhere, and what his health is always number.max value. So a simple workaround is to store the state on the server and play the game simultaneously on the server as well as playing it locally. The problem with that is that the player's local position, as shown on the left side circle, and then the player's blue position is where the player is actually located. And as you can see, your projectile on your screen will appear to have hit this player, but it will go right through them because on the server, that player is no longer at that position. This is actually obviously a very large problem because it happens in reverse. You might be moving, and then a projectile will kill you, and you clearly dodged it, but it's because what you see on your local version of the game does not match what is going on the server right now. Another problem with this approach is sometimes referred to as the bouncing ball problem. And that is that if, as we receive new position and new information regarding the velocity of the entity from the server, we draw that entity with this information, and it causes abrupt shifts in motion along the projectile's path. In this chart, the dotted lines represent discrete information received from the server at regular intervals. And if we draw the player's path using the instantaneous velocity at that given point, the path takes very abrupt, sharp edges, and it's incorrect and incorrect until it receives new, more up-to-date information, at which point that red line will now move along that path at that velocity, and it will continue to be incorrect and incorrect, and then switch again when it receives new information. And you get a very zigzag style motion that appears on the screen. The blue line represents the player's actual movement. Let's see. Of course, this time is measured in milliseconds, so a common solution is to decrease the sampling rate on the server side so that players receive more information about their world state, and that same chart will happen again, but it happens at such small incremental spaces that it's hard to visually notice the problem. This is only an even more naive solution because most of the time you cannot have that kind of message throughput to all clients at all times unless they're all on OC3s. So we took a different approach. This is actually quite common approach in multiplayer games, like on consoles, or Source Engine comes to mind. Originally, it came from Quake World. And so I decided to look around and see how other people have been doing this, because creating multiplayer games, real-time multiplayer games, has been being done for a while. And I found some interesting information. The Quake World source code is open source, along with several of the other Quake games. And Valve also has some white papers regarding networking in real-time games. And in this approach, the single authoritative server is this represents one tick on the client side and the server side. In this approach, the server will process inputs, move the objects, update the game simulation, create a single snapshot, and then let its server net channel do what it needs to do. I'll explain what that means later. On the client side, it's actually only responsible for two things. One of them is to sample the user intervals at a discrete rate and then render the world. The benefit of this approach is that you can have a really, really, really interesting game, and because all of that logic and the entire simulation happens on the server, you can really go apeshit with what your game can do. You can have physics on top of other things and various things, and every single browser that's playing the game sees the same thing, regardless of whether their browser can keep up with a two-dimensional rigid body physics simulation and display a canvas element with 100 objects. It doesn't matter because they're only in charge of displaying the object. And everyone's simulation also magically kind of lines up. Our nervous system is designed to work around latency. We're very good at that. So if we can apply a smooth, constant latency to an object's path, human beings can adjust to that very well. So the key piece of the puzzle, where I sort of started to have the eureka moment of this as I was going through the Valve source papers, is that we actually simply render all the clients n milliseconds in the past. So I'm just going to call that number 75, but it's just an arbitrary number. And that's what this is. The current time on the client side is shown over here. So we can say that the current time is about 10.46 seconds. Now we render the world at 10.32 seconds. Those triangles represent world snapshots that we've received from the server. So the first thing that we do is we find the value for the rendering time, which is the current time minus some number. Then after that, we loop through the existing world snapshot updates that we have from the server, and we find two that we fall in between. And now that we have found those two world snapshots, using a simple linear interpolation function, we can precisely place our object at its position along that path. Another benefit to this approach is that if one of those packets were dropped, for example, if we did not have packet 342, we could still interpolate between packets 341 and 343, and the user will end up in their correct location. So it's actually a pretty good protector against packet loss, and it actually assumes that packets will be lost, and the system can bounce back from that. So we decided that this was a pretty interesting idea, and some of these concepts would help JavaScript game developers. So we abstracted these concepts from our game, and we created a framework for them. And I'm going to show you a demo now. All right, so let's see. I'm going to start the server, and then open up my browser, and let's see. Can't see that. There we go. All right, there we go. So this, besides being pretty, is actually running, hold on, I cannot see my screen. There you go. This will have to do. Where's my, okay. So this actual simulation is running on the server. Where's my little character? That's me as I'm moving around my keyboard. Those entities are being controlled on the server. So I'm going to try, I'm having a little bit of computer problems here, but I'm going to try to open up this in a different tab. So here we have synchronized multiplayer activity going on, and see if I can make this guy show up there. And then the other large circle is somewhere else on the screen. I can't really find him. So the way that the engine works is that everything that you're seeing is actually happening on the server, and the server simply sends world snapshots to all of the clients. So everyone is guaranteed to be in sync at the same time. It does add a little bit of latency towards your movement by default, because you're always rendering n milliseconds back in time. But human beings are very good at adapting to that. It's better to render a little bit behind in time and adjust to that lag than it is to constantly have abrupt changes in motion. And then the other benefit is, because it is running on the server, and this is a little bit of a cooler demo, we can show, if I can find my mouse. Where's my mouse? Okay. Oops. Because it is running on the server, I'm going to fire up the other demo that I have, which is actually a Box 2D implementation that was ported to JavaScript, and it's actually really well done. Let's see. Oh. And I'm going to try to time these because it looks really, really cool in the beginning, so let's see if I can pull that off. This and I didn't pull that off. I can't. Sorry, I can't find my mouse. There you go. All right. Let's try one more time. I'm just going to drag this like this. There you go. So this is an example of a Box 2D simulation that is being run on the server, and the clients are being told where these objects are, and they are interpolating between any of the two positions. And this helps you get really fluid motion. The cool thing about that is that I'm going to join, or try to join, with a different browser. So here's an instance of Firefox. And I'm going to join this game. And now we have synchronized physics across two different browser instances that are playing the same game. And it's actually running at a pretty good frame rate in Firefox and pretty much the same frame rate in Chrome. And the simulation is running on my computer in Node.js, but I'm going to also try to see if I can get Safari to do this. 3 browsers might be a little bit too much for my computer, but we can give it a try. There you go. So now we have all 3 main modern browsers running the same physics simulation. There we go. Cool thing is, so here's some interaction between I'm sending my information to the server, and then it's playing the game. I think my computer's kind of messing up a little bit. And then that's just a demo of the Box 2D implementation that is built in with the library. No. And then the last thing I want to show, I don't know if I'm over on time, but I wanted to show that the small amount of code that it takes to get something like that up and running. Let's see. So for this demo, I have I can never seem to find my mouse on here. There we go. So ignoring the framework, I'm going to show just these few files that I have. And basically, the demo app is just a namespace. Then I have a file that has a couple of constants in there for me. So the main 2 points of entry for using this library are the demo client game, which is what the browser will display, and the demo server game. This is where all your cool stuff goes. So the demo client game doesn't really have too much to it. It has a setup view function. Real-time multiplayer NodeJS is agnostic to whatever view you would like to use, so it could be Canvas or something else. It has a simple tick function which gets called, and it has this function which, once the engine detects a new entity, it will tell you, hey, create an entity from this description. That description has some properties that are passed to it from the server. Then you can have some callbacks for when connection happens, when it disconnects. You don't actually have to do anything with these at this point. And then the server game, all that's going on here is I create a new instance of the collision manager. This is just actually a very simple radius-based collision manager that I created that does provide group masking so that, for example, my projectiles don't hit anyone else's on my team's projectiles. So it initializes that, creates a few entities, and then calls tick. And then these are the callbacks for the network. So that's about it. And that amount of code will get you running with the first demo. The Box2D demo has a little bit more things in it, but they're all related to Box2D. And this framework is live on GitHub as of a few days ago. So I work for Ogilvy. That's it. Thank you.